Okay. So I was reviewing 4.4's video on Canvas, and there were a couple of minor errors I made with some of the work on some of the examples. Perhaps I wasn't as specific as I could have been, or I just decided to reevaluate the work I did. But I want to re-upload a video, and I want to look at this example. This is the first page of 4.4 notes. And then we're going to look at another example in the same notes. And they're minor little changes, but I do want to talk about them. So, if you remember this model, right? This, we were doing quadratic modeling, or building quadratic models from descriptions and data. So the first example was an example of a quadratic model from a description. And if you use the revenue equation and you're given a demand equation, X is the number of calculators sold, and this is the demand equation where P is the price of the price per calculator or per unit. So to find the equation, to find the revenue function as a function of price, well, by definition, revenue is equal to X times P. And since my revenue has to be a function of P only, I need to replace X with the equation for P. So this will become 18,750 minus 125P times P. And if you distribute the P there, you're going to get 18,750 P minus 125 P squared. So that is my revenue function. If I write that in standard form, that's negative 125 P squared plus 18,750 P. That's my revenue as a function of price. That's it. That was okay in the video that I did earlier. I mean, there's nothing wrong with that. It's the same thing. But number 2 is where I kind of deviated a little bit. In that video, I mentioned the domain of the revenue function was 0 to infinity, when in reality, I mean, I suppose in some context that is true, but I could have been more specific with that, and for some reasons I wasn't, because it involved doing something that you would see in the next section, 4.5. So I'm just going to do it though, because it's really not that hard. So the domain of the revenue function, well, we know the revenue function. I'm just going to copy it down. And we know that revenue must be positive. Revenue must be positive. It doesn't make sense for revenue to be negative. Revenue can also be 0. So this description right here, revenue must be positive, could also be 0. That could be described as the inequality greater than or equal to. Right? So what I could do is I could say that my revenue then, which is right here, negative 125 P squared plus 18,750 P, could be greater than or equal to 0. If it's positive, it has to be greater than 0. If it's 0, it could be equal to 0. So if I solve this quadratic inequality, then I could find the domain of my revenue function. So solving quadratic inequalities was the topic in 4.5, but it's really not that bad. So the way you're going to solve this is, well, you're going to factor it first of all. Now I know I had it factored here, so I'm just going to write down the factors. I already had that here. So you're going to factor it. So when you do factor, you're going to get P times negative 125P plus 18,750. And that's greater than or equal to 0. So now that this is factored, right, you're going to set each factor greater than or equal to 0, just like you would if it were a quadratic equation. It's the same thing. So that means P is going to be greater than or equal to 0, or negative 125P plus 18,750 is greater than or equal to 0. So this inequality right here is already solved for P. That means that now P stands for price, right? Because this is a function of price. So this means that the price should be at least 0, right? Obviously that's true, right? Something could be free or it has to be charged something. You can't have a negative price. That doesn't make sense either. But here's the other inequality. So, just solve this for P. So subtract 18,750 from both sides of the inequality. All right, so now you're going to get negative 125P is greater than or equal to negative 18,750. Now, if you divide both sides by negative 125, well, you're going to cancel out. You're going to get P. Now, because I divided by a negative number, my inequality flips, right? So greater than or equal to becomes less than or equal to. And negative 18,750 divided by negative 125, if you do that in your calculator, it's 150. I already did it in my calculator because I did it earlier. But so the combination of these two inequalities is the domain for my revenue function. So if I draw a number line and I graph those two inequalities on my number line, so 0 is over here, 150 is over here, right? So if I graph P is greater than or equal to 0, well, that means I have a solid dot at 0, and that's going to be everything to the right of 0. And it keeps going forever and ever, right? That's how you would graph P is greater than or equal to 0 on a number line. Now, if I were to graph P is less than or equal to 150, that means 150 has a solid dot, and everything to the left of 150, forever and ever. So the combination of these two inequalities would be the shaded region in common. So if you look at the shaded region, right, this piece right here in the middle between 0 and 150 is the shaded region in common. So that would be the domain. That would be the domain of this function. The common area between 0 and 150 is the common area for these two inequalities. So that would be the domain of the function. So my domain of R of P, and if I use inequality notation, that's just 0 to 150, and those two values are included. That's it. So, yeah, a little minor change, but that is how you would do that problem. The other mistake, or the other change I wanted to do, was on page 3 of these notes. It was the projectile problem. So, just to refresh your memory, this is a function that measures the height, which we call h of x, of the projectile. So, if somebody's throwing a football or whatever, here's the horizontal distance. Somebody here's throwing a football, right? They're going to throw it. It's going to reach a height, and then it's going to come down. So that parabolic shape can be modeled by h of x. X is the horizontal distance of the projectile from the firing point. So if somebody here is throwing a football, then from here to where the football hits the ground, that's the value of x. Now the height is just, that's just the height of the projectile. That's how high it can go. All right. So question one was correct in the original video. There's no change there. That's perfectly fine. So question one was saying find the maximum height of the projectile. Well, so height is the h of x value. All right. X is the horizontal distance value. So the independent variable was x, right? That's the distance. It's the horizontal distance. And the dependent variable was h of x. That is the height of projectile. Right? So if I'm trying to find the maximum height, that means I'm trying to find the maximum h of x value. Right? I'm trying to find the maximum y coordinate of this parabola. Well, we know from properties of quadratics that if the leading coefficient of a quadratic is negative, which it is here, there's the negative sign, that means my ends, my tails are pointing down, which means the maximum point is the vertex is a maximum. And we know how to find the vertex of a quadratic. It was given to you in their notes. So yeah, the leading coefficient is negative, which means the tails are pointing down. So the vertex is a maximum in this case. So the maximum would be the maximum height. The y coordinate of the vertex would be the maximum height of the projectile. So we just need to find the vertex so we need to find the x coordinate of the vertex, and then we need to plug it into the function to find the y coordinate. So the vertex as an ordered pair is negative b over 2a, comma, and then you plug it into your function at negative b over 2a. So we're interested in this coordinate right here. That's what we're interested in. That'll answer question one. So letter A, the leading coefficient is negative 32 over 10,000. Letter B is 1, and letter C is 100. So in the video, I went through that. Work, and there's nothing wrong with letter number 1. When you go through that work, right, the x coordinate. So when you do that, you're going to get negative 1 over 2 times negative 32 over 10,000. And if you do that computation, you get roughly 156.25. Now that's the horizontal distance from the firing point where the projectile is at a maximum, right? So if you're thinking about throwing a football, if you throw it on the 50-yard line, it might reach the maximum at the 25-yard line. So that would be 25 yards away from where you threw it. So that's what this value represents. But we want the maximum height, so you're going to take that and plug it into h of x. So the y coordinate of the vertex will be h at 156.25. And if you pop that into your function, which you could use your calculator for, right, the function is parenthesis negative 32 divided by 10,000 parenthesis x squared plus x plus 100 So ignore that number. Don't worry about that. Just store 156.25. Store that in the x. And now, when I retype that equation and hit enter, I get 178.125. So 178.125 that is the maximum height of the projectile. In other words, this ordered pair, 156.25, 178.125, is the vertex of this quadratic model. Now, question 2, that's I might not have gone through the computation in this video, but if you follow that in the other video, it's this is essentially correct. This is essentially the same as that. Now, number 2 is where I kind of goofed. I kind of said that number 2 was this result, but it's not. This is, like I said earlier, this is the horizontal distance from where the vertex would be located, right? That's where the maximum height would occur. That's how far away you are horizontally from where it would occur. So it would be right there, right? If you threw it from here, this horizontal distance here would be 156.25. But what this problem is saying is how far from the firing point will the projectile hit the ground. So when the projectile hits the ground, right, if I go back to my quadratic picture, right, the projectile is going to hit the ground. Technically, it's going to come up here and then it's going to come down. The football, if no one catches the football, it's going to hit the ground, right? It's going to hit the ground at this point right here. So if this is my projectile, someone throws it and it comes down again. Here's the ground, right? This might be my vertex, but the projectile is going to hit the ground at this point right here. And that's where it hits the ground. So how do I answer this question? Well, how far from the firing point? That right there is talking about the value of x. So they're saying, what is x when, and this says the projectile hits the ground. So that's talking about h of x. Well, what's the value of h of x when my projectile hits the ground? That's, h of x measures height. So if it hits the ground, then the height is 0, right? So that's what this is saying right here. That's when it hits the ground. So all you're doing is you're going to set this quadratic equal to 0. The height will be 0. So this means you're going to set and solve for x. And when you do that, technically you're going to get two values, right? You're going to get this value and you're going to get this value right here, because a parabola can have two values. But you'll see in a minute that only one of these values will make sense. So if you set my quadratic, which is negative 32 over 10,000 times x squared plus x plus 100 equal to 0, that's just a quadratic equation in standard form. I would not attempt to factor that because of this big ugly value. Obviously you would not factor that. I wouldn't even complete the square on that. But you could use the quadratic formula. So you just have to be a little careful, right? A here is negative 32 over 10,000. B is 1. And C is 100. So the quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Just take it one step at a time. So I'll do the numerator over here, or well, I'll do this little term over here separately. I'll just do it piece by piece. So So I'm going to have negative 1 plus or minus square root of b squared, so that's going to be 1 squared minus 4 times a, which is negative 32, that's the big ugly value, over 10,000 times c, which is 100. Alright, let's simplify this down as much as we can. So 1 squared is 1, obviously. Now I have a minus times a plus, which gives me a plus. Right? Now 4 times 32 times 100 is going to be what? 4 times 32 times 100 is 12,800 divided by 10,000. Gives me 1.28, which if I use a fraction there, that's going to be 32 over 25. Okay, so I guess I don't need as much square root, do I? That's going to be that. Now I'm going to have negative 1 plus or minus the square root. Now remember, you can't break this up. You got to add everything under here. So 1, I could write 1 as, I could just treat this as 25 over 25, right? 25 over 25 plus 32 over 25. Will give me 57 over 25. So I'll have the square root of 57 over 25. All right. Now don't forget, this is just the numerator of this problem. So there's that. Let me come over here. So I'm going to have negative 1 plus or minus. Now if I simplify the square root here, I could just write this as the square root of 57 over the square root of 25. But the square root of 25 is 5. So that's nice. All right. And so this is what the numerator the numerator becomes this. Okay. Now the denominator is 2 times a. So this is all going to be over 2 times, now a was the negative 32 over 10,000 value again, which is nice. So 2 times negative is negative 64 over 10,000. Which is negative 4 over 625. Alright, let me get rid of that ugly thing. So to bring this up, just multiply it by the reciprocal. So I'm going to have 625 over 4 times the numerator, which was negative 1. Oh wait, this is still negative, sorry. I'm going to have negative 625. Again, I'm just taking to bring this up, you just take the reciprocal. So I'm going to have negative 625 over 4 up top times the numerator, which is negative 1 plus or minus the square root of 57 over 5. So I have two values here, right? I have this number times negative 1 plus the square root of 57 over 5, and this number times negative 1 minus the square root of 57 over 5. I have that number, and I have that number. So here's where we're going to have to do some approximation. These two values are going to be the two values here. Okay, let's do the first one. You know, you're not going to get nice numbers when you do quadratics sometimes. You just don't. So, -1 plus parenthesis square root of 57 divided by 5. Right, -1 plus the square root of 57 divided by 5. That gives me that. Times that by the fraction -625 divided by 4. And that gives me approximately -79.68. Now let's do the other one. So I'm going to have -1 minus second, parenthesis, second square root of 57 over 5. All right, that's the that's this part right here. -1 minus square root of 7. So that gives me that. And then multiply that by negative. So times that by that times parenthesis -625 divided by 4. And that gives me 300. My video froze. There it is. That gives me 392.18. So which one do you think I care about? Remember, we're trying to find how far from the firing point will the projectile hit the ground. So technically these two values, the -79.68 is right here, and the 392.18 is right here. This is the one I care about. I can't have a negative distance, so I don't care about that one. But I do care about this one. So the answer to the question, how far from the firing point will the projectile hit the ground? Well, the answer will be roughly 392.18 feet. And if you were to type this quadratic in your calculator, right? So negative parenthesis -32 divided by 10,000 parenthesis x squared plus x plus 100. Let's graph it. I might have to adjust my window. I only care about positive values. Well, let me go. So there we go. There's my projectile somewhat. I just need to get most of it in. Go out there, zoom in there a little bit, and then I'll zoom out from there. I just want to get both intercepts in the view. There we go. That works. So both intercepts. So let me check this intercept right here. So second calc, that's the 0 value, right? That's the x-intercept. So the left bound, right bound gives me 392.18. Hey, there we go. So that right there is where the projectile hit the ground, which is exactly what we got by hand. You just gotta take your time with the quadratic formula. But that's it. So that's how you would answer that question. So those are the only two little goofs I made, but other than that, everything else should be fine. So, you know, once again, I do somewhat apologize for that, but yeah. So those are the edits to those examples in the 4.4 notes.